So there's an increasing need for understanding the risk of environmentally induced damage due to fluctuations in humidity and temperature. And however, studies based on the use of mock-ups mimicking historic materials are often questioned in relation to the artificial aging scheme employed, as well as the mock-up composition adopted. Nanoindentation is a small length scale mechanical characterization technique capable of direct examination of sub-millimeter samples, which may be obtainable from real objects in some cases. Nanoindentation also opens an opportunity for more comprehensive analysis of historic oil paints with enigmatic local heterogeneity, such as metal soap formation and metal-ion migration, and so forth, known to have detrimental effects on the artworks. So nanoindentation involves pressing a conical or more typically pyramidal indenter into the sample surface while recording the load applied and the resulting displacement continuously throughout the loading and unloading cycle. And assuming that the unloading response is fully elastic, it determines the elastic stiffness of the sample as the slope of this unloading curve at the beginning. And the reduced elastic modulus, which is basically equivalent to an elastic modulus, is given as the stiffness normalized to the contact diameter, or 2 times the contact radius, A. And this A contact radius is obtainable knowing the geometry of the indenter and the contact depth. And contact depth is calculated from this equation, where you have the depth and the load and the stiffness at the beginning of the unloading, thanks to the work of Oliver and Farr. And the nanoindentation can be operated in dynamic mode. And so, yeah, by superimposing a small amplitude oscillation on the gradually increasing load. And this gives us an opportunity to monitor the stiffness continuously throughout the loading process. And this feature is quite useful when you don't know whether you're testing homogeneous system. In this case, we are looking at a change in elastic modulus as a function of depth. And so this dynamic indentation also allows us access to viscoelastic properties of the materials. And the principle is identical to DMA, but a lot of experts of this technique have already covered this topic. So I'm going to the next slide. So here we have embedded globally homogeneous acrylic paint of about 200 microns in thickness. Which is here. And it's supported by a resin of 10 times higher stiffness. And what I'm doing here is to make indents very close to the edge and also away from edge, and comparing the mechanical response. So what I have here is on Y is the stiffness versus depth. So when you are indenting a position, a location, the sample at the location away from edge, you have this linear relationship between stiffness and depth. And this slope of the constant line gives a constant modulus. Whereas if you go close to the edge, this relationship becomes nonlinear because of the edge effect that I'm going to cover in the next slide. And in testing a lot of samples in this cultural heritage field, we also have to deal with the effect of surface roughness, which dominates at the beginning of contact. And often, there's a limit as to how shallow you can make an indent in a meaningful way, because this roughness effect masks the intrinsic property of the material. And okay, so nano-indentation always assumes that the volume of indent you are creating is much smaller than the volume of the sample that you want to test. But often in this cultural heritage field, the materials available from real objects is so tiny that you have no choice but to go very close to the edge. And yeah, so in this example, so the indent positioned close to the embedding resin, which, by the way, has a 10 times higher stiffness, is the displacement of material in this region is restricted by this higher stiffness of the surrounding material. And by a distance Cp, where C is the structural compliance and the P is the load. So the good news is, if you know this value of structural compliance in this situation, you can still measure the mechanical properties of the material by using H star and S star described by these equations. And there are two ways that we are aware of in determining this value of compliance. And the one method proposed by Jakes and his colleagues assumes the ratio of square root of contact pressure to modulus to remain constant with depth. Whereas our model based only on the constant modulus with depth. There are some reasons why we are adopting this assumption that I will touch on later. But yeah, so, but the issue with our model is that you have to solve a more complex equation with three variables, whereas for Jake's model, you only have a single constant. So it's very easy to solve this equation. But we have a reason for doing something more complex, which I cover later. And so this shows the obtained storage modulus as a function of depth. And the top is the results without making any correction, and the modulus evaluated at a very small force or small depth. And as you go close to either edge, you can see the modulus being higher than elsewhere. And although the sample is supposed to be homogeneous, globally homogeneous acrylic paint. And so this default method is suffering the effect of the edge. Whereas if we use our model, you get the constant modulus profile across the thickness of the film as expected. And here we are now moving into a more realistic system. So what we have is the Verdigris oil paint film casted 25 years ago. And so this is the optical image of the surface, and this is the scanning electron microscopy. And okay. If you enlarge the individual indentation sites, you can see that there are many cracks. We don't know whether they existed before indentation or occurred during indentation, as well as some gaps between some of the pigments and the binding material. And the black region is the binding material, so some particles, pigment particles, were supported predominantly by the more compliant binding material. And so what we saw in the previous slide is a very complex system, but we believe this complex system reduces to a more simple two-material system with multiple compliance sources resulting from those cracks, and also the presence of more compliant material surrounding the most stiffer copper acetate particles. And also we have, as always, we always have this surface roughness in cultural heritage samples. And we know how to deal with this surface roughness by introducing this conceptual effective contact point, H0, which is often different from the machine-detected 0 point. So you see this effective contact point in our equation here. But if you look at this, our model, you notice that there is only a single compliance element, although we know that there are multiple compliance sources, one resulting from crack in the pigment, and another is due to the interface to this more compliant binding material. And there may be the third one that's due to the gap between particles or interface to a binder. So, so our approach, so although this model takes only one compliance term, we can assume that this model describes the system until you go deep enough so that you are triggering the effect of the secondary compliance. So, or until such time that the effective sampling volume of experiment exceeds the actual volume of the particle, in which case you're supposed to have a different modulus. That is more and more dominated by the underlying binding material in this case. So, so I'm showing this example of indentation made on this particular particle. And you can see that this is the stiffness versus contact depth, and you can see a nonlinear curve with a distinctive curvature in one direction. This is resulting from compliance, presumably, of this crack here, because this is where we indented, and the crack is so close to the indentation site. But then as you keep pushing this deeper, you begin to feel the effect of the surrounding binding medium, which is in the black color. And this second compliance source gives you a negative sign because of the relative difference between the two systems. So what you have here is the stiffness versus contact depth of the same experiment that you just saw, but with this analysis range varied 3 differently. I'm fixing the beginning of the analysis range the same for 3 cases. By the way, so this initial region excluded is because of the surface effect, mainly the surface roughness effect. And as you move this upper boundary of the analysis range, you can see that the RMSE, or the error of the model, increases. Actually, in these 2 cases, error is identical. By the way, the compliance and the modulus values are also identical. But if you go beyond about half micron in this particular case, you have an increase in not only the prediction of the model, but also a change in the compliance and elastic modulus. And I'm plotting here the compliance versus contact depth and of many analyses with varied upper limit of this range. And you can see that initially, although at the very beginning, when the upper limit is set to very low value, close to origin, you have no choice but to see some, fluctuation, because there are only, so many data points, and particularly close to the surface, your data is more affected by the surface roughness. But as you go deeper, you begin to see this stabilization of the compliance. But then if you go beyond half micron, you begin to see a decrease of the compliance. And this eventually goes to a negative value, although we didn't go that far. And the same applies to modulus. You see a flat modulus profile up to certain depths, beyond which you begin to feel the effect of the underlying material. Oops. And so, yeah, so we had 8 indentation experiments from this sample. And the 2 of the 8 were excluded because the load, the stiffness versus depth curve indicated the possible adhesion of the binding material on the tip. Before performing those 2 experiments, the indenter was used to study the properties of the binding material. And the remaining 2 of the 4 excluded the cases had asymmetrical pattern, asymmetrical shape of the residual indent on the surface. And actually, one of them had the asymmetrical indentation, and the other case had a strange, like a bump in the curve. So they are also excluded. So for those 4 indentation sites, we are able to identify a region of constant compliance. So we analyzed the data at the depths beyond which compliance begins to fall or rise due to secondary compliance taking effect. So, yeah, so this is the modulus of the 4 indentation sites as a function of, in this case, I plotted it as a function of contact radius, because you can then relate the indentation size to the actual size of the sample. And you can see that the modulus of those particles were quite consistent, whereas the hardness of the same materials were basically the same, but not necessarily the same for all cases. And in one case where the effect of the underlying binding material, which is more compliant to the pigment, was, I think, playing a role of reducing the effective contact pressure. And getting back to the very initial point, the basis for our model, which does not assume anything about the hardness, because we know that the hardness, if you are working with such a complex system in cultural heritage field, cannot be always assumed constant. And so surprisingly, I was surprised to see that we were able to measure the properties of such a small particle. This is like 20 microns in size, and the cracks and we only discovered how the surface looked after Alexandra taking SEM image. And yeah, and so we believe we have a system or a method to deal with realistic materials in the cultural heritage field. And so I'm over time? Or? Yeah, okay. Thank you, yeah.
Thank you, Naoki. I didn't mean to cut you that brutally, but I understand that you come to the conclusions of the talk. So thank you very much, and I would like to open the floor for the discussion. Do we have any questions?
Hi, I've got a question about specifically this. So obviously, when you're looking at a cross-section, you see only the polished surface, and you're seeing the grain from the top. And pigment grains are irregular, so you don't really know how much material there is under the surface, right? So can you tell from your results when you hit a pigment grain that essentially was just the thinnest possible layer that you could see, and you're actually not pushing the pigment, but the medium underneath?
Sorry, I couldn't hear clearly, but so you're talking about whether we have the ability to measure the properties below the particle, particularly in this case.
If I may try to clarify, I think that the question is, and correct me if I'm wrong, is that the particle itself can be very shallow, and we will have a different material below, and how the model is dealing with such a situation. Can we still measure the mechanical properties of the particle? Is it right?
Yes, and also, like, can you tell the difference when you're hitting a particle that is an anomaly in a sense because of it?
Okay. Yeah, so if you have that situation where the particle has a very small depth, then you would feel more of the effect of this compliance resulting from this interface to more compliant material. So I think this, so this is probably the example. And of course, we monitor the compliance, and if the compliance behaves strangely, which happens in other cases. And then that's when we exclude the results rather than trying to interpret it.
So if I can maybe add to that, I think that the whole idea is that the model which Naoki presented is working when the compliance can be presented by constant, which reflects interaction of two systems. So if we start to see that the compliance starts to change, then we see that there is influence of the other system, and there is the kind of indicating the limit of the measurement. Mm-hmm. Do we have any other question?
It's a very general question. There's a lot of time-dependent information in some of these experiments, stress relaxation, and do you have any general comments about the prospects for getting viscoelastic information quantitatively?
Yeah. Although in this particular case, we focused on the property of copper acetate particles, which are not really viscoelastic. But the model looks at the storage component of the stiffness. And the acrylic paint work that we did prior to this work was really about dealing with the viscoelasticity and this concept of, the assumption of constant hardness is really not working for such a viscoelastic material. And so this model actually is a result of us considering viscoelastic system.
And some of the motivation of this work was then when we are trying to compare in different scales properties of the materials, we found that in the macro scale, or this meso, like DMA scale, the properties of materials were governed mostly by the binder, whereas in the indentation we found those very different situation, and we started to think whether it is actually possible to characterize components of the material, which could be useful information for example, modeling of the behavior or generally understanding the historic materials. Cecile?
I'm thinking maybe just a short comment that we were looking into micro-CT scanning of some of these samples to understand what we're actually looking at and how shallow are the pigments and so on. I don't know if you have any comments on that, but I just thought that could be a promising way of analyzing understanding our results.
Yeah, I think just to fully convince ourselves that our measurement or the model is working, such information is very useful. Yeah.
Okay, let's thank Naoki once more time. Thank you very much.
Thank you.